All right, let's talk about tangents and normals. We talked about these before. We have found the equations of tangent lines and normal lines. One of the nice things about calculus is that there are so many practical applications. And tangents and normals are interesting because if you think about a lens, um, if you take a point on the lens and find the equation of the tangent line, and then you find the equation of the normal line, it turns out that if you're talking about refraction, you're talking about light coming in at some sort of angle. The bend in the light, which is known as refraction, is calculated using this angle right here, the difference between the normal at that point and the incoming light. So this is one where it actually can is used quite a bit in calculations. So let's just dive right in and take a quick look at an example. This is wow, my writing today? It's not great. Example 4. We have an elliptical lens, and our elliptical lens has the equation x squared minus xy plus y squared equals 7. And we're interested in the tangent and the normal at point -1, 2. So obviously, we're already struggling to solve this for y, to write it as an explicit equation. We could theoretically use the quadratic formula, but we're not gonna. Instead, what we're gonna do is we're going to, step 1, take the derivative with respect to x. So we've got 2x minus, well, now we're gonna need right here a product rule. U is equal to x, v is equal to y, the derivative of u is 1, the derivative of v is dy dx. And so coming back here, we've got minus u dv xy prime plus v du, which is just y. And I'll switch back to black. Plus the derivative of y squared is 2y times the derivative of y, and it equals the derivative of 7, which is 0. So step 2, we're going to collect all the dy dx terms on one side. So I've got minus xy prime. Notice how much easier it is to write this when I just write y prime and I don't have to write a whole bunch of dy dx's, plus 2y dy dx, or y prime, equals, and I'm going to subtract the 2x, and I'm going to add the y. Notice this is a minus y. So now, step 3, I'm going to factor out the derivative of y with respect to x. I'm left with minus x plus 2y. And over here, I've got minus 2x plus y. And then I solve for the derivative, and I get y at minus 2x divided by 2y minus x. I switch them around because I find it easier, but the positive terms first. And I want to know the equation of the tangent line and the normal line at this point. And what I get is that the derivative, so this implies that the derivative is equal to, just checking my notes rather than recalculating, 4/5. All right, so let's write the equations. Remember, point slope form is the easiest way to write the equation of a line. So my tangent line is y minus 2 is equal to 4/5 times x minus -1. And my normal line going through the same point is y minus 2 equals opposite reciprocal minus 5/4 times x plus 1. Have to be a little bit more careful if you put them into y equals mx plus b form, which is why I like point slope so much. So Why don't you guys go ahead and do exercise 17, and you can pause the video. All right, welcome back. Let's look at higher order derivatives. And higher order derivatives, it's just do it twice, but there's a little bit of a twist when we're dealing with implicit differentiation, and I'll show you the twist. So here we go. 2x cubed minus 3y squared equals 8. And to find the first derivative, we'll just do all the steps. I got 6x squared minus 6y times the derivative of y equals 0. Now, here's the trick, the tricky part. I could do this a second time. I'm going to take the derivative with respect to x, and I get 12x minus 6 times. Now I've got to do product rule. So u dv plus v du. And when I solve for the second derivative, I'm going to get that it is a function of x, of y, and of y prime. I have all of these things. There's x's, there's y's, and there are y primes. And this is a problem because when I'm dealing with a math problem, I'm going to be told find the value at the point x and y. So now I've got to go back, and I've got to go back to here, and I'd have to take my x and y, and I'd have to have that written down, and I'd have to solve for the derivative in order to plug it into the final. I want to be able to say the answer to my problem is, and give one equation and say, there it is, there's the answer. So what I am going to do instead is I am going to, at this point in the problem, I want to say this point, I mean at this point in the problem, I'm going to veer off, and I am going to solve for the first derivative. And what I get is that the first derivative is x squared divided by y. So instead of doing this and getting the second derivative as a function of the first derivative, meaning I have to continually work with two equations to calculate that first derivative in order to find the second derivative, I'm just going to find the derivative of that. It's still implicit, but it's quotient rule. So here we go. The first derivative is x squared over y. Quotient rule, u is equal to x squared, the derivative of u is 2x. V is equal to y, the derivative of v is the derivative of y. So the second derivative is equal to, well, v du, so 2xy minus u dv, which is y prime times x squared, u dv, v du minus u dv, yes, all over v squared. Well, I still have the problem. I'm not just thrilled with the way I went there because I just realized something. I could have just done that step and gone back. Foolishness. Okay, let's continue. I'm going to substitute this right into here. So I've got that the second, and I'm going to go back and I'm going to show you what I just realized I should have just done. The second derivative is 2xy minus x squared over y times x squared, all divided by y squared. And if I do a little simplification, I get 2xy over y squared is 2x over y minus, combining all this stuff together, I get x to the fourth over y cubed, and there's the second derivative. So let's go back, because honestly, I could have done the exact same thing here. I've got, and I'm going to just change colors. I'll change to gold. I've got 12x minus 6 times y double prime plus, well, I know that y prime is x squared over y all squared is equal to 0. And so it wasn't really that much simpler. I just sort of was like traipsing along with the book and not really thinking, which is my fault. So solving this, what do I get? I'm going to subtract 12x, divide by -6, and I get that y times y double prime plus x to the fourth over y squared equals 2x. Uh, y times y double prime equals 2x minus x to the fourth over y squared, and then dividing everything by y, I get 2x over y minus x to the fourth over y cubed. I got the same answer. And I think the reason the book walks it through this way, and I should have given this more thought to begin with, is that simplifying at a simpler step, simplify first. The idea is that if you simplify and then do the next step, you don't run yourself into a hole where the second derivative is so complicated. In this case, it really wasn't too bad. I think it was a little bit more complicated. And when we look over here, it's a pretty straightforward quotient rule problem. So I would say that in general, let's go with what the book says, which is 1, find the first derivative, 2, solve for y prime, and then 3, take the derivative again of that. And maybe you just don't run into so many issues. But okay, there you go. Hopefully that didn't confuse you too much. If you're in my class, why don't you go ahead and do exercise 29. And I'm going to stop this video and come back with a little fun aside.